Good day and welcome to Mathgic, a webinar where we'll focus and showcase basic calculus tutorials. Today's class, our agenda are to discuss limits, derivative by definition, basic rules of derivatives, and additional rules of derivatives. Let's start.
Hi, I'm Magician Lawrence. Today I'll be discussing about limits. Let's start.
This is Lawrence Mesana. We're gonna tackle limits and we'll see what it means, and how do we solve for this. Limits is defined using notation here, where f of x is a function of x and c is an element of real numbers. So we can read this notation as the limit of f of x as x approaches c is equal to L, or limits. Next. So we can estimate the value of limits through the table of values. So we have an example here, and this one. Uh, so this one is our equation, our function. So this one is our c, and this one is our left hand side. So we will we can get the value of limits by means of substituting the x value to this function. So if we substitute 1.999 to to x, so the values in the result is 4.998. So on the left hand side, our value will be less than 2 but closer to 2. So yeah. The next is 1.99. The result of it is 4.98. The next is 1.9. The result of it is 4.8. So that's the left hand side. So the next is right hand side. Right hand side is the of the value, greater than the value of c, which is 2. So, but closer to the value of c. So we have 2.1, 2.001, 2.01, and 2.1. So when we substitute this or evaluate this here in our equation, we will have 5.002. In 2.01, we will have 5.02. And in 2.1, we will have 5.2. So as we can see on this table, we can say that the estimate value of limits is equal to 5. So, yeah, 5. So next. So the one side limit. So there are two types of limit. There are two types of side limit. So we have left hand side, which is less than the value of c, but closer to the value of c. So on our first example on the table of values, is our left hand side, limits of 2x plus 1 as x approaches 2, less than 2 is equal to 5. And our right hand side is greater than the value of c, but closer to the value of c. So on our first example, we will have this solution. Limits of 2x plus 1 as x approaches 2 greater than 2 is equal to 5. So you can say that the estimate values of our first example is equal to 5. So next. So next is our next example is limits of 3x plus 4 as x approaches positive 2. So we have example. So this is the the left hand side because it has a negative exponent, which means less than the value of c. So in, um, our x will be 1.99. The next is 1.99, and then the last is 1.9. So we will have the value of y, or the value of limits, by means of uh, substituting this x, or the value, to our equation. So when we substitute that, we will have 3 times 1.999 plus 4. So we will have 9.997. So on the next one, we'll have 9.97. And to the last one, when we substitute, we will have 9.7. So we can say that the limits of 3x plus 4, or as x approaches 2, less than 2, which is our left hand side, equal to 10. You can estimate it. I mean, these are estimated values in our left hand side. So next one. So we have the right hand side of our example. So we will have x and y. So the next example, we will have uh, our value of c, but greater than the value of c. So we'll have 2.001. Next is 2.01. And the last is 2.1. So when we substitute this value to our function, we will have uh, 10.003. The next one is 2.01. We will have 10.03. In the last one, we will have 10.3. So we can say that the limits of 3x plus 4 as x approaches 2, but greater than 2, is equal to 10. So yeah. So we can say that the estimate values of our new example, this one, our function, we can say that our estimate values is equal to 10, estimating limits from the graph. So here, we have a new example here, a graph. We can estimate it by just looking at this point. So we can say that this graph is equal to is limits of f of x as x approaches -4, here -4, that one, -4, is equal to 3.3. The limits is equal to 3.3, here 3.3. So next, let's move on. So we can look at this one first. We can look at the left hand side, which is the limits of f of x as x approaches uh, positive 3 but less than. So can say that limits of f of x as x approaches less than 3 is equal to positive 4. So that is our left hand side. So on the right hand side, we have the limits of f of x as x approaches positive 3 but greater than 3. We can say this is equal to negative 3. So if the left hand side is and the right hand side is not equal, we cannot estimate its value. So it is undefined. Yeah, that's undefined. So summary of limits. So recap number one: limits is defined using the notation. So we can read this notation as limits of f of x as x approaches c is equal to limits or L. The next one is recap number two: limits can be estimated using the tables. We can estimate the limits by using the table of values as we do earlier, as we solve the left hand side and the right hand side, less than the values of c but closer to c, and the right hand side is greater than the value of c but closer to c. So recap number three, we need to consider the left hand side and right hand side limits. So we need to consider them both because some example have undefined, also undefined. If if uh, if we are not considering this both, we cannot estimate the exact value of the limits. So recap number four: when the left hand side and the right hand side limit is not equal, then the limit of the function does not exist. So we have an example earlier on the graph. Uh, our left hand side and right hand side is not equal, so the limit of the function does not exist because we cannot estimate its values and they're not equal. So that's so that's all. Thank you.
Hi, I am Mathgician Miguel, and I'll be discussing limits part 2. And come on, let's start. Hi, I'm gonna start. My name is Miguel Reyes. The limits part 2. Limits at infinity is solved using the notation in the left. Limit of f of x up as x approach positive infinity equal to L, or limit of f of x as x approach negative infinity equal to L. Limits at infinity. The table of values is the one way to solve for the limit as it approach infinity. This is the given example, and to solve this is gonna be the limit of x cubed plus 2x minus 5 as x approach to positive infinity. And to solve this is just follow this. 0 cubed plus 2 times 0 minus 5 is equal to negative 5. Then next, 10 cubed plus 2 times 10 minus 5 is equal to 1015. And then 30. 30 cubed plus 2 times 30 minus 5 equal to 27,055. Then 50 times cube plus 2 times 50 minus 5 will be the 125,095. And lastly, the 100. 100 cubed plus 2 times 100 minus 5 is equal to 1,195,000. And the final answer will be the limit of f of x as x approach plus positive infinity equal to infinity. And then let's go to my example. This is the example I have. So I'm gonna solve my example. This will be the limit of 3x cubed plus 2x plus 3 as x approach to positive infinity. Go. When we substitute the 0 to x, the answer will be the 3. The answer will be 3. When we substitute the 10 to x, the answer will be 3023. When we substitute the 30 to x, the answer will be 81,063. When we substitute the 50 to x, it's gonna be 375,103. When we substitute the 0 to x, when we substitute that 100 to x, it's gonna be 3,203,000. So the final answer is gonna be the limit of f of x up as x approach positive infinity is equal to infinity. This one. Next topic, the rational function. Rational function is defined as the ratio of two polynomials. This one, m of x and n of x. This is the numerator and this is the denominator. There are three cases in the rational function. The first case is gonna be the limit of a rational function as it approaches to infinity is equal to the ratio of the leading coefficient of numerator and denominator. I have an example for that. So my example is gonna be 6, the limit of 6x squared minus 4x plus 9 over 4x squared minus 5x plus 1. This is gonna be 6 over 4 because the leading coefficient is the leading coefficient is squared. So 6 over 4 and lowest term is gonna be 3 over 2 or Next, case 2. The limit of a rational function as it approaches infinity is equal to 0 when the degree of numerator is less than the degree of denominator. I have an example for that. The limit of 3x plus 2 the limit of 3x plus 2 over x squared minus 4x plus 5 as x approach to negative infinity. This is gonna be 0. Case 3. The limit of a rational function may be equal to positive or negative infinity when the degree of the numerator is the greater than the degree of denominator. I have an example for that. So to solve this, it's gonna be x minus 1 to x minus 2 x minus 2 and copy the denominator. This is gonna be cancel, and the x minus 2 is the last. So the limit of x minus 2 as x approach negative infinity, the final answer is gonna be the limit of x approach negative infinity is equal to infinite negative. Now let's next slide. The summary of limits part 2. Let's recap number 1. The limits at infinity is solved using the notation. This is the limit of f of x approach positive infinity is equal to L, or limit of f of x as x approach negative infinity equals to L. Creating a table of values is one way to solve for the limit as it approaches infinity. And rational function is defined as the ratio of two polynomials. Then we can use case 1, case 2, and case 3 when solving for the limits of a rational function as it approaches infinity. Actually,
Hi, I'm Mathgic Kylie, and today I'll be discussing derivatives. Let's start. Now, let's move on to the derivatives part 1. We have here the derivatives, which says that it is defined using the notation in the left. This notation is read as f prime of x. Wait, I'm going to use a so we can follow this. F prime of x is equal to the limit of f of x plus h minus f of x all over h as h approaches 0. Now we're gonna have our first example. We have to solve for f prime of negative 2 given the function f of x equals to x plus 5. So obviously, we're gonna solve this using the derivatives by definition. You can see here in the right, these are the steps in solving the problem. So we need the derivatives by definition, which is f prime of x equals the limit of f of x plus h minus f of x all over h as h approaches 0. According to the first step, which is substitute the value of x to the equation. We're gonna have f of negative 2 plus h minus f of negative 2. Then the second step, we have to evaluate the function with negative 2 plus h and negative 2. These are the ones being mentioned. So we're gonna have, if we evaluate those, we're gonna have 2 multiplied or times the quantity negative 2 plus h plus 5 minus the evaluation of f of negative 2, which is 2 times negative 2 plus 5 all over h. Next step, we have to distribute the constant and perform necessary operations. When we distribute here the constant 2 and the quantity, we're going to have negative 4 plus 2h plus the term outside, which is 5. Then if we distribute 2 to negative 2 here, we're going to have plus 4, since negative of negative 4, we're going to have positive 4 minus positive 5. So we have minus 5 all over h. The next step is to add all the constant terms. As you can see here, we have negative 4 and 4, which will equate to 0. Also 5 minus 5. Therefore, we're left with 2h, all over h. You can see that there is a common factor in the numerator and the denominator, which is h. If we cancel it, we'll be left with 2. Therefore, our answer is f prime of negative 2 is equal to 2. Next example, we have to solve for f prime of 3, or rather f prime of negative 3, given the function f of x equals 5 minus 2x. We're gonna solve this using the derivative by definition, which is f prime of x equals to the limit of f of x plus h minus f of x all over h as h approaches 0. We have to substitute the value of x in the equation, which is 5 minus 2x. We're gonna have f of negative 3 plus h minus f of negative 3. If we evaluate those two, we're gonna have 5 minus 2 times the quantity negative 3 plus h minus 5 minus 2 times negative 3. Then we need to distribute the constant terms here, which is 2 here and another 2, and do necessary operations. So we're gonna have 5 here, which is the outside term. We'll just copy it. We're gonna have 5 here, and then we'll distribute negative 2 in negative 3 plus h. We're gonna have plus 6 minus 2h. And the other one, we have 5 minus 2 times negative 3. We're gonna have negative 5 minus negative 6. Minus 6 rather. All over h. We have to add the constant terms, which are 5 minus 5, which will equate to 0. Also 6 minus 6 is 0. Then we are left with negative 2h all over h. As you can see, the numerator and the denominator has a common factor, which is h. So we can cancel it. We will be left with the limit of negative 2 as h approaches 0. So our answer is f prime of negative 3 is equal to negative 2. Next, we have 5 basic rules of derivatives. The first one is the constant rule, which states that the derivative of any constant is equal to 0. Next, the identity rule, which states that the derivative of any identity function is equal to 1. The third one is the constant multiple, which states that the derivative of a function that has a factor c is equal to the derivative of the function multiplied by c. Fourth rule, we have the power rule, which states that the derivative of a variable raised to n is equal to n multiplied by the variable raised to n minus 1. The last rule is the addition or subtraction rule, which states that the derivative of a multiple functions or terms being added or subtracted together is equal to the sum or difference of the derivative of the equations or terms. We're gonna understand these rules more by examples I'll be giving. The first one is we have to solve for 18dx. We're gonna solve this using the first rule, which is the constant rule. The answer will be 18dx equals 0 because we only have here the constants 18, and the derivative of any constant according to the constant rule is 0. Next, we have to solve for RDR using the identity rule, which states that RDR will be equal to 1. Next example, we have to solve for 10x dx. We will solve this using constant multiple, which states that the derivative of the function x dx is multiplied to the factor of c, which is 10. So according to the identity rule, x dx is equal to 1. Therefore, we have 10 times 1, which is 10. Next example, we have to solve for 3x squared dx. We're going to solve this using the power rule. According to the power rule, the derivative of this is n times the variable raised to n minus 1. So our n here is the exponent, which is 2. So we have 2 times 3 and x raised to 2 minus 1, which is equal to 6x raised to 1, or 6x. Our last example is 3x squared. We have to solve for 3x squared plus 5x minus 1 dx. We're going to solve this using the addition or subtraction rule. Using this rule, we have to get the derivative of each term of this function. So we'll have 3x squared dx plus 5x dx minus 1x dx. Or 1 dx rather. So the derivative of the first term, which is 3x squared, we're going to use power rule, which will give us 6x. While the second term, we're going to use the constant multiple, which will give us 5. And the last term, which we're going to use constant rule, which will give us 0. So we have here 6x plus 5 minus 0, or 6x plus 5. Now, we have to summarize our discussion. Our first recap is derivatives is defined using the notation f prime of x equals to the limit of f of x plus h minus f of x all over h as h approaches 0. And aside from using the derivative by definition, we also have 5 basic rules, which are the constant rule, identity rule, the constant multiple, power rule, and addition or subtraction rule. That's all.
Hi, I'm Mathgic Aubrey, and today I will be discussing derivatives. So let's start. So hi, I'm Aubrey, and I'll be discussing derivatives part 2. So excluding the 5 basic rules of derivatives, there are still 3 additional rules left, and these are product rule, quotient rule, and lastly, the chain rule. So let's start with the product rule. So this is how product rule works. The derivative of the product of f of x and g of x is equal to the sum of the product of f of x and the derivative of g of x and product of g of x and the derivative of f of x. So this is the equation of product rule that we are going to use. So let's have an example. Let's say we have here 3x minus 4 times 5x squared plus 2x plus 1. So the first thing that we're going to do is let's get the f of x and the derivative of g of x. So let's get the f of x. So the f of x of this function is 3x minus 4. So let's just copy it. 3x minus 4. And then next is let's get the derivative of g of x. So this is the g of x, the second function. So by the way guys, when solving a product rule, make sure that we have 2 functions. So in this case, we have 2 functions, this one and this one. So let's get the derivative of g of x. So the derivative of 5x squared plus 2x plus 1 is 10x plus 2. So after that, we are going to get the g of x and then the derivative of f of x. So plus, let's just copy the g of x. So 5x squared plus 2x plus 1. And then let's get the derivative of 3x minus 4. The derivative of 3x minus 4 is 3. So yes, after that we are going to expand this. When expanding, we are just going to multiply this to this and this to this. So let's multiply. 3x times 10x is equals to 30x squared. And then 3x times 2 is equals to 6x. Next is negative 4 times 10 is equals to negative 40x. And then negative 4 times 2 is equals to negative 8. There. Next is this one. So 3 times 5x squared is, wait, let's put at, so 3 times 5x squared is 15x squared. And then 3 times 2x is equals to 6x. And 3 times 1 is equals to 3. So this is not yet the final answer. We still have to simplify it and be able to get the final answer. So when simplifying, we just need to combine the like terms. So 30x squared plus 3x squared is equals to 45x squared. X squared, and then 6x plus negative 40x plus 6x is equals to negative 28x. And then negative 8 plus positive 3 is equals to negative 5. So this is the final answer. The quotient rule. So quotient rule. Let f and g be a function that is differentiable at c. So this is the equation that we are going to follow and use. So to make it easier, we can just use LDH minus HDL all over L squared. So low is high times the derivative of low all over low squared. So let's have an example. So we have here 5x squared minus 2x plus 1 all over x minus 5. So let's follow the LDH minus HDL all over L squared. So first, we're going to get the low part, which is x minus 5. We're going to put it in the numerator. And then the next is the derivative of high. So the derivative of 5x squared minus 2x plus 1 is 10x minus 2. After that is minus high. So let's just copy the numerator, which is 5x squared minus 2x plus 1, and then the derivative of low, which is 1, all over low squared. So we're just going to copy this. And then put squared or raised to 2. There. After that, we are going to expand the numerator. So as what I said earlier, expanding means multiplying. So x times 10x is equals to 10x squared. X times 2 is equals to x times negative 2 is equals to negative 2x. And then negative 5 times 10 is equals negative 5 times 10x is equals to negative 50x. And then negative 5 times negative 2 is equals to positive 10. On the other hand, 1 times 5x2 is equals to 1 times 5x squared is equals to 5x squared. We're just going to copy this since we are just multiplying it into 1. So 2x plus 1. And then copy the denominator, which is x minus 5 squared. So after that, we're going to simplify. So by the way, this is already negative. So we're going to change the signs of this function, since when we combine negative and positive, it would be negative. And then when we combine negative and then negative, it would be positive. And then negative, positive is negative. So let's simplify. 10 plus negative 5x is equals to 5x squared. And negative 2x plus 2x is equals to negative 50x. And then 10 plus negative 1 is equals to positive 9. Wait. Oh my gosh, it's so hassle when you don't have a mouse. All over, let's just copy the denominator. So x minus 5 squared. So this is the final answer. So next is the chain rule. Let f and g be a function that is differentiable at c. Chain rule is normally being used to differentiate composite function. The equation of chain rule. So let's have an example. So we have here 6x minus 3 raised to 4. So in chain rule, we need to get the let u first. So the let u is the inner function. So the inner function, it is the function inside the parenthesis. So the inner function here is 6x minus 3. So let's copy it. Wait. So let u is equals to 6x minus 3. So next is we need to get du. Du is the derivative of let u. So the derivative of 6x minus 3 is 6. So after that, we need to substitute. So we have here u for du. Then let's get the derivative of u raised to 4 is 4u raised to 3. Then du. So after that, let's substitute again. So we're going to put this to the value of u, and then the du is 6. So for 6x minus 3 raised to 6x minus 3 cube, then the value of du is 6. And then after that, let's multiply 6 and 4. So 6 times 4 is 28. No, 6 times 4 is 24. So 6 times 4 is 24, and then let's just copy this. Minus 3 cube. So this is the final answer. 24 times 6x minus 3 cube. So next is the trigonometric function. So the trigonometric function are sine x, cosine x, tangent x, secant x, cosecant x, and cotangent x. So these are the trigonometric function. So in trigonometric function, we have identities that we need to familiarize or we need to memorize, since it has a big role when solving. So this is the reciprocal identities. This is the quotient identities. And the Pythagorean identities. The double angle identities. Then these are the derivatives of trigonometric function. So yeah, let's have an example. So let's say we have here sine times 6x. So in this case, the process that we'll be using is chain rule. So first is we need to know the let u. As I said earlier, the let u is the inner function. So the inner function here is 6x. Let u. So the inner function is 6x, and then next is the du. The derivative of 6x is 6. There. After that, you need to substitute. So sine u du. So we need to get first the derivative of sine. So the derivative of sine is cosine x. Cosine. So let's put here cosine. Cos u, then d u. So let's substitute again. Let's put the value of let u here and then the value of du here. So cos then 6x and then 6. So let's multiply this and this. So it will become 6 cosine times 6x. So this is the final answer. There. Let's have another example. Say we have here let's say we have here 4 cosine x minus 2 sine x. So in this case, we'll be using the addition and subtraction rule or process. So first is let's get the derivative of cosine x. So the derivative of cosine x is negative sine x so the derivative of cosine x is sine x. So let's copy the 4 sine x and then let's get the derivative of sine x. Wait, I forgot to put x here. There should be x here. So derivative of sine x is cosine x. So plus 2 cosine x. So this is the final answer. There.
To summarize the discussion of Miss Aubrey for the derivatives part 2, we have our first recap. As you can recall earlier, I have discussed 5 basic rules. So aside from those, we have 3 additional rules of derivatives, which are product rule, quotient rule, and chain rule. And when we are solving for the derivatives of trigonometric functions, we can use the reciprocal identities, quotient identities, Pythagorean identities, and double angle identities that was shown earlier by Miss Aubrey. And that's it. We're done for today's webinar. Until next time, fellow magicians.
This is where our webinar ends. We hope that you learned a lot about limits and derivatives. Again, this has been Mathgician Aubrey.
And this Magician Lawrence.
And this, Mathgic Miguel.
And I'm Magician Kylie.
Thank you for joining us today, and we hope to see you again next time on another Mathgic basic tutorial video. Thank you.
Bye!
Bye.